1.495 respectively. Calculate the critical angle, the acceptance angle and the numerical aperture. Actually with for the critical angle we have the equation sin phi c equal to mu1 by mu2 by mu1, or you can say it is n2 by n1, and the acceptance angle we have just now derived the equation, that is theta in max or say phi in max equal to the sine inverse of under root of n1 square minus n2 square, and na is simply sine of this acceptance angle. So the answers are 75 degree 23 minutes, 22 degree 56 minutes, and the numerical aperture of that particular fiber optics cable is 0.3896. Now also we can experimentally determine the Na of the given cable with a different equation that depends upon the width and the distance from that particular cable to the screen. Now we will determine it experimentally. Here is a fiber optic cable, and we can see it, we will see it after some time, but if you can see the light intensity, it is gathering from this LED source, right? I am just showing you initial LED, which now I am launching the light into this cable, and you can see the light intensity at the another end of the cable. This is done with the total internal reflection. And now I'll show you, I'll demonstrate you how we can find out the numerical aperture of this fiber optics cable. Okay, now we will move to the another table. As I shown you, there is a light beam coming from this fiber optics cable, and actually due to these lights we cannot see it properly, but there is very faint intensity. Actually what we have to do here is scale in centimeter from 1 to 7 centimeter, which is the length, which shows the length, and here is the diameter of this particular circle, and there are 4 circles with different diameters. So what we have to do, we have to just focus this light intensity onto these circles by keeping this, say I'll put it like this way, by keeping this in mind that this intensity should be focused on one of the circles. I am focusing the intensity on the first circle, and after that I'll measure the distance. As say first circle has the diameter of 10 millimeter, I'll measure the distance from the fiber optic cable to the this particular diameter plate, and that distance shows the L, and the diameter is W. And with this we can have in the equation we can put the values, and we can find out the numerical aperture W with W and L. And this numerical aperture can be compared with the theoretical values of core and cladding with the refractive index N1 and N2. And this plays a very important role. Actually, if you have the experimentally measured numerical aperture, then you can find out the core and cladding refractive indices, as well as some another properties like attenuation of the fiber optics, that particular fiber optics cable. Now the classification of the fiber optics cable. There are actually basically three major criteria. First is RI profile, that is refractive index profile. Second is the modes of propagation, and third is the material of which the fiber optic cable is made. This is actually the broadly classified table based upon the three criteria. First is based on the RI profile, that is step index fiber. Second is green fiber, that is graded index fiber. The second criteria is based on the material. There are actually three types of fiber optic cable: glass, plastic glass, and plastic fiber optics cable. This shows that in core material there is glass, in cladding material there is glass. When PCS, when we say that plastic clad silica, then cladding is of silica, and the core is of plastic material. Based on the modes, there are two types. First is single mode, another is multi-mode fiber optics cable. Now, what is modes of propagation? When we say that modes of propagation in the fiber optic cable, the modes can be visualized as the possible number of allowed paths of light in a fiber optics cable. If the core has very smaller diameter, very less diameter, then it will not be allowing much light to be launched inside the cable. That means only one ray at a time can be processed inside the cable, and that is called the single mode fiber optic cable. But when it allows number of rays at a time at a particular time, then there will be a multi-mode fiber optics cable. If there is, as I said, if there is only one path for light to take down in the cable, it is called the single mode. If there is more than one path, it is called the multi-mode. What is RI profile? Refractive index profile. It is a plot of refractive index drawn on one of the axis and the distance from the core on the another axis. Now, there are two basic types of index profiles: step and graded. Step means it is the stepwise index profile. One can say that it has a central core with a uniform refractive index. The core is surrounded by an outside cladding with a uniform refractive index less than that of the central core. This means that from the core refractive index, the transition from the core refractive index to the cladding refractive index is discrete. The N1 and N2 values are entirely different, and one can see here that the refractive index profile is totally different. Now, in a graded index fiber, there is no cladding, and in a way the refractive index of the core is non-uniform. From the axial center, there is the increase in the refractive index occurs. The maximum value of the refractive index occurs at the center, and then it reduces radially. It is highest at the center and decreases gradually with the distance towards the outer edge. And at the cladding, it is having the value of the refractive index of cladding N2. One can see here the cross-sectional view as well as the refractive index profile. Now, what is graded index fiber and what is step index fiber? One can see in this link. See, this is the step index fiber. How it works? It gives a perfect angle of reflection at the core cladding interface. We can see a perfect zigzag pattern inside the core. But here in the graded index fiber, But in the graded index fiber, the reflection occurs due to the gradually changing reflective index, and we cannot have this type of perfect pattern. Now, what is a single mode fiber? One can say that this is the single mode. This is only one way communication, only one ray can be processed at a time. And moving ahead, we can have single mode step index fiber. As we have seen in this animation, it has a central core that is sufficiently small, so there is essentially only one path that light may take as it propagates down the cable. And in the refractive index of the cladding is slightly less than that of the central core, and it is uniform throughout the cladding. Consequently, all light rays follow approximately the same path down the cable and take approximately the same amount of time to travel the length of the cable. So this is the single mode, this is the result of the single mode optical fiber. The laser signal, that is the input signal, and the received signal, they are almost one and the same. So it is a high fidelity fiber. Now, in the multi-mode step index fiber, what happens? The light rays that strike the core cladding interface at an angle greater than the critical angle, they are propagated down the core in a zigzag fashion and continuously reflecting. There are many paths that a light ray may follow as it propagates down the fiber. As a result, all light rays do not follow the same path and hence do not take the same amount of time to travel the length of the fiber, and that's why you can see the modal dispersion in this type of multi-mode step index fiber. The light signal is both signals are Gaussian curves, but the real one, the initial one, the input signal is quite different from the output signal, so it has a bit of distortion in the received signal. So you have to make attenuation correction in the output. Now we can have the comparison of the three important fiber optical types. Step index single mode fiber, this is called SSSI. Small diameter having 10 mm. The numerical aperture is very small. One mode support is there, so at a time only one signal can be processed, but the attenuation is very less, that is, it is the high fidelity fiber. The laser diodes are the source. Laser diodes can be used as the source for this type of step index single mode fiber. It is used as underwater cables. It is highly suited for communication because of least attenuation and no degradation of the signal. Now, second is the step index multi-mode fiber. It is a small core diameter 50 mm, but it is high compared to the first one. The NA is larger compared to the first one, of course, and multiple mode support is there, so attenuation is very high, and LEDs can be used as the source. They are used in data links, or say launching of light is easier because of the high or say larger acceptance cone, and due to that feature, actually easy coupling can be done. Now the third one, that is graded index multi-mode fiber. Core diameter is of the order of 50 mm to 100 mm. The numerical aperture is very small. Multiple mode support is there, of course, but attenuation is medium, and LEDs are the source. It is used in telephone links. LED or laser source can be used, and coupling and manufacturing is very difficult. What is attenuation? The attenuation says that the light signal through the fiber suffers from a loss of amplitude, attenuation, and change in the shape distortion. So whenever there is a loss of amplitude during the core cladding interface reflection, it is called the attenuation, and if the shape is changed in between the input and output, then it is called the distortion. Attenuation is defined as the ratio of the optical output power from a fiber of length L to the input power. Say alpha is the attenuation constant, that is called alpha, the unit is in decibel per kilometer. So for fibers unit length, one can find out the power attenuation constant in terms of the decibel. It is 10 by L log of pi upon p0. Actually in Bell, if you do not multiply this with 10, then the unit will be in Bell per kilometer. But for a real time situation, the Bell unit is very high, so that's why we are using the unit as decibel. For it is again, you must have reminded the first chapter where you have found this decibel unit for your intensity level, and this loudness level or say intensity level or loudness level you are measuring in terms of decibel, nothing more than that. It is similar to the intensity level. There you were taking the sound power ratio, here you are taking the ratio of the optical power output and the input again it is optical. Now for ideal fiber, this fiber attenuation constant is 0. Why? Because for ideal fiber the input and output powers both are same. Now another example, the optical power of 1 millivolt is launched into a fiber of length say 100 meter. If the power emerging from an other end is 0.3 millivolt, calculate the attenuation constant. Using this equation one can easily find out the attenuation constant in dB per kilometer. When you put this input power and output power in this particular formula, you can get the answer as 52.3 decibel per kilometer. Of course, don't forget to say convert your 100 meter unit into the kilometer. Now how can we fabricate the fiber? One can see there are two major methods. There are apart from these two major methods there are another methods also, but these two are widely used in industries in the fabrication of fiber. First is double crucible method. You can see the schematic diagram of the double crucible method. Actually there are two crucibles in which the inner crucible has core glass and the outer crucible has cladding glass, and with this Foram there is a fiber drawing machine which winds the fiber onto one another, core and cladding, and this with this cladding field rod and core field rod one can feed the core and cladding material inside these two crucibles, and here is the fiber optic cable which can be made. The second is vapor phase oxidation process. Actually it is nothing but the vapor phase deposition. Fiber preform core and cladding material, drawing furnace is here, and thickness monitor coating application is here. One can coat the curing oven, and here is the take up drum. So from here one can take away the newly born fiber glass, say you can say it is a newly born. Now what are the advantages of optical communication? Why should we have optical fibers as the communicators in place of our conventional copper wires or say iron wires? They have extremely wide system bandwidth. That means they can carry a large amount of data at a time with less attenuation. Second reason is immunity to lighting, electric motor